There's a moment just after the sun sets when the sky transforms into a vast, twinkling canvas, a silent spectacle of stars stretching farther than the eye can see. But what if I told you that those pinpricks of light are just the beginning? Beyond them lies a cosmic labyrinth, a maze of galaxies, dark matter, and phenomena so strange they challenge everything we think we know about the universe. Welcome to a journey where the rules of physics bend, where black holes might not be cosmic dead ends but doorways, and where entire galaxies move in ways that defy explanation. This is Inside the Cosmic Labyrinth, decoding intergalactic mysteries, and today we're pulling back the curtain on the universe's most baffling secrets. Think about the last time you felt truly small under that starry sky. Now multiply that feeling by a trillion. Out there, in the depths of space, there are forces at work that make our planet, our solar system, even our Milky Way, seem like specks of dust in an endless ocean. Take dark matter, for example, an invisible scaffold holding galaxies together, yet we've never seen it directly. Or consider the eerie whispers of alien megastructures, hypothetical constructs so massive they blot out stars, leaving astronomers scratching their heads. These aren't just science fiction, they're real puzzles waiting to be solved, and they're rewriting the textbooks as we speak. So why does any of this matter? Because every time we unravel one of these cosmic riddles, we're not just learning about distant galaxies, we're learning about ourselves. The universe is a mirror, reflecting back the limits of our knowledge and the boundless potential of human curiosity. And that's what this journey is all about. From the mind-bending physics of black holes to the tantalizing possibility of other dimensions, we're diving headfirst into the unknown. By the end of this video, you'll see the night sky differently, not just as a blanket of stars, but as a living, breathing mystery, inviting us to explore deeper. Ready to decode the cosmos? Let's begin. The cosmic labyrinth isn't just a poetic metaphor, it's the perfect way to describe how the universe operates on a scale so vast, it reshapes our understanding of reality itself. Imagine standing at the entrance of an endless maze where the walls aren't made of stone, but of swirling galaxies, invisible dark matter, and the gravitational pull of black holes so strong they warp time around them. Each corridor of this labyrinth leads to another question. Why do galaxies spin faster than they should, as if tugged by unseen hands? What causes the universe to expand at an ever-accelerating rate, defying gravity's grasp? These aren't just curiosities, they're clues woven into the fabric of space, waiting to be untangled. Take dark energy, for instance, a mysterious force pushing the cosmos apart. Scientists estimate it makes up nearly 70% of the universe, yet we know almost nothing about it. It's like trying to map a maze while blindfolded, relying only on echoes. Then there's quantum entanglement, where particles separated by light years react instantaneously, as if distance means nothing. Albert Einstein famously called it spooky action at a distance, and decades later, it still baffles researchers. These phenomena aren't isolated oddities, they're threads in the same cosmic tapestry, hinting at deeper laws we've yet to uncover. What makes this labyrinth so fascinating is how it forces us to rethink the tools we use to navigate it. Traditional physics, which works flawlessly here on Earth, starts to crumble at cosmic scales. It's like using a candle to explore a cavern. The light only reaches so far. That's why astronomers and physicists collaborate across continents, building telescopes that peer back in time and particle colliders that recreate the universe's birth. Every discovery, from gravitational waves to rogue planets drifting between stars, adds another turn to the maze. And just when we think we've found a way out, the universe reveals another layer, another question begging to be answered. This is the thrill of the cosmic labyrinth. It doesn't just test our knowledge, it tests our imagination. Whether it's the possibility of parallel universes or the search for extraterrestrial intelligence, each mystery pulls us deeper into the unknown. And that's the beauty of it. The universe isn't a puzzle to be solved once and forgotten. It's an endless conversation, a challenge that keeps us reaching further, dreaming bigger. So as we venture deeper into this labyrinth, remember, every dead end is just a new beginning in disguise. Picture this: you're holding a snow globe, watching glitter swirl around a tiny winter scene. Now imagine that glitter is invisible, you can't see it, but you know it's there because the snowflakes move as if pushed by unseen hands. That's the strange reality of dark matter. It doesn't glow, reflect, or absorb light, yet its gravitational fingerprints are everywhere. Galaxies spin so fast they should fling stars into the void, but something invisible grips them tightly. Light from distant galaxies bends as if passing through an invisible lens. The cosmos is teeming with this ghostly substance, yet after decades of searching, we still can't say what it actually is. Some scientists believe dark matter could be weakly interacting massive particles, hypothetical bits of matter that barely interact with normal atoms except through gravity. Others propose actions, ultra-light particles streaming through space like an intangible cosmic breeze. Then there's the mind-bending idea that dark matter might be gravity itself leaking into our universe from a parallel dimension, like ripples from a pond we can't see. The possibilities stretch our imagination to its limits. What makes this hunt so thrilling is how it forces us to innovate. Deep underground, in abandoned mines shielded from cosmic rays, detectors wait patiently for the once-in-a-lifetime collision between a dark matter particle and ordinary atoms. In space, telescopes like Euclid map the invisible scaffolding of dark matter by watching how it distorts the light of millions of galaxies. Even the Large Hadron Collider smashes protons together at nearly light speed, hoping to create dark matter in miniature Big Bangs. Here's what's truly humbling. Everything we can see, stars, planets, even ourselves, makes up less than 5% of the universe. Dark matter outnumbers normal matter 5 to 1. It's the silent architect shaping the cosmos, weaving galaxies into vast web-like structures across billions of light years. Without it, the universe as we know it wouldn't exist. Yet this mysterious substance remains just beyond our grasp, a cosmic riddle written in gravity's faint whispers. Every failed experiment, every unexpected result isn't a dead end. It's a signpost pointing toward new physics. The day we finally capture dark matter won't just solve a puzzle. It will crack open a new window into reality itself. Until then, this invisible giant continues to dance just beyond the edge of our vision, reminding us how much we have yet to discover. If dark matter is the universe's invisible glue, then dark energy is its mysterious opposite, a force so relentless, it's pushing the cosmos apart faster than gravity can pull it back together. Back in 1998, astronomers made a discovery that shattered expectations. Distant supernovae were dimmer than they should have been, meaning the space between us and them was stretching at an accelerating pace. The universe wasn't just expanding, it was in a hurry, as if some unseen hand had pressed down on the cosmic gas pedal. This revelation flipped our understanding of gravity on its head. Einstein's equations had always suggested the universe's expansion should slow over time, like a ball rolling uphill. Instead, we found it was more like a ball rolling downhill, gaining speed when it should be losing it. The culprit, dark energy, a repulsive force making up nearly 70% of the universe's total energy. But here's the twist, we don't know what it is. Is it a property of empty space itself, a constant energy woven into the fabric of the vacuum? Or could it be evidence of something even stranger, like a parallel universe gently tugging at the edges of our own? The implications are staggering. If dark energy keeps strengthening, it could lead to a big rip where galaxies, stars, and even atoms are torn apart in a cosmic crescendo of expansion. Picture a loaf of raisin bread baking in an oven, but instead of the raisins staying put, the dough stretches so violently that every raisin is ripped from the others. That's the nightmare scenario dark energy might one day unleash. Yet for all its destructive potential, dark energy is also a puzzle that's driving some of the most ambitious science of our time. Telescopes like James Webb and the upcoming Nancy Grace Roman Space Telescope are scanning the depths of space, mapping how galaxies cluster and how light bends over billions of years, searching for clues in the subtle warping of spacetime. Meanwhile, theorists are wrestling with ideas that sound like science fiction extra dimensions, quantum fields we can't yet detect, or even the possibility that our universe is just one bubble in an infinite cosmic foam. What makes dark energy so fascinating isn't just its power, but how little we understand it. Every observation, every calculation, feels like trying to decipher a message written in invisible ink. And that's the beauty of this cosmic mystery. It reminds us that the universe is still full of surprises, still capable of defying our best theories. Whether dark energy is a fleeting phase or a permanent fixture of reality, one thing's certain, the cosmos isn't just expanding. It's running away from us, daring us to catch up. Now imagine floating in space, watching as not just one or two galaxies drift by, but thousands, all streaming in the same direction like fish caught in an invisible current. This isn't science fiction, it's the reality of the Great Attractor, a gravitational enigma lurking beyond the Milky Way, yanking entire galaxies toward it at a staggering 14 million miles per hour. And here's the twist, we can't even see it directly. Our own galaxy's thick dust clouds block the view, leaving astronomers to piece together clues like detectives solving a cosmic crime. What could possibly wield such immense pull? At first, scientists thought it might be a supercluster, a dense knot of galaxies with gravity strong enough to tug on everything around it. But as telescopes peered deeper, something stranger emerged. The Great Attractor isn't the end of the story. Behind it lies an even larger structure, a sprawling wall of galaxies nicknamed the Laniakea Supercluster, a Hawaiian word meaning immeasurable heaven. This vast cosmic web stretches over 500 million light-years, with the Great Attractor acting like a gravitational pit stop along a much grander highway. Then there's the wild card. Could this be the work of something even more exotic, like a cosmic string? These hypothetical scars from the early universe, thinner than an atom yet denser than a neutron star, might warp space-time around them, creating gravitational anchors that pull in everything nearby. Or perhaps dark matter is clumped here in ways we don't yet understand, sculpting a hidden landscape of gravity wells. What's truly humbling is how this mystery reshapes our place in the cosmos. We're not just orbiting the sun or drifting through the Milky Way, we're part of a much larger flow. A celestial migration driven by forces we're only beginning to map. Recent X-ray observations reveal hot gas ribbons stretching toward the Great Attractor, tracing the outlines of this invisible river. It's like watching leaves swirl in a stream, knowing there's a waterfall just beyond sight. The Great Attractor does more than defy maps, it defies our expectations. Every time we think we've grasped the universe's scale, it whispers back, look deeper. Whether it's a supercluster, a cosmic string, or something beyond our current physics, One thing's certain: the cosmos loves a good plot twist, and as long as mysteries like this linger, the universe remains the greatest story ever told, with chapters we've only just begun to read. One moment the cosmos is silent, the next a flash of radio waves brighter than 500 million suns erupts across the universe, then vanishes without a trace. These are fast radio bursts, or FRB, some of the most baffling signals ever detected. Lasting just milliseconds, they arrive from galaxies billions of light years away, carrying enough energy to outshine entire stars. Some burst once and never return. Others repeat unpredictably, like a cosmic Morse code with no sender. And despite catching hundreds of these signals, we still don't know what's creating them. Take the infamous FRB 1212, for example. Discovered in 2012, it wasn't just powerful, it repeated. Unlike one-off bursts, this one flickered on and off like a malfunctioning beacon, sparking theories from colliding neutron stars to alien megastructures. Then there's FRB 1809, which pulses with eerie regularity every 16 days, as if set on a cosmic timer. Such precision in the chaos of space is unsettling. What natural phenomenon could possibly keep a schedule across billions of years? The leading suspect: Magneta's super-dense, highly magnetized neutron stars spinning so fast they could power a city with a single twist. When their crusts crack under intense magnetic pressure, they might unleash bursts of radiation visible across the universe, but not all FRBs fit this mold. Some are too energetic, too erratic. That's where wilder ideas come in: cosmic strings, hypothetical defects in spacetime left over from the Big Bang, snapping like overstretched rubber bands. Or perhaps black holes slurping up nearby matter, creating shockwaves that ripple across the cosmos. Then there's the elephant in the room: could FRBs be deliberate? The notion of alien origins isn't as far-fetched as it sounds. A sufficiently advanced civilization might use focused radio beams to propel spacecraft, creating flashes detectable across the universe. Or maybe they're cosmic lighthouses meant to announce their presence. The truth is, every explanation feels like grasping at stardust. Even with telescopes like CHIME scanning the skies 24/7, cataloging hundreds of bursts, the pattern remains elusive. What makes FRBs so thrilling is their sheer unpredictability. Each detection is like finding a single puzzle piece from a box scattered across the galaxy. Some bursts are polarized, their radio waves twisted like a corkscrew, hinting at turbulent magnetic fields. Others arrive with a telltale smear, stretched out by the cosmic gas they've traveled through, offering accidental maps of the universe's hidden matter. This isn't just about solving a mystery, it's about rewriting the rules. Every burst challenges our understanding of physics, pushing us to imagine phenomena wilder than fiction. Whether they're the death cries of stars, the snap of cosmic strings, or something beyond our current science, FRBs remind us that the universe is far stranger, far louder than we ever dreamed. And with every new signal, the cosmic labyrinth grows deeper, its walls echoing with questions we've only just begun to ask. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, and yet we've never heard a single whisper from another civilization. This eerie silence is the heart of the Fermi Paradox, a question that has haunted scientists for decades. If the cosmos is so overflowing with potential for life, where is everybody? Named after physicist Enrico Fermi, who famously asked, "Where are they?" during a casual lunchtime conversation in 1950, this paradox exposes the unsettling gap between our expectations of a crowded universe and the reality of our cosmic solitude. Consider the numbers for a moment. Our Milky Way alone holds an estimated 100 billion planets, many in the so-called Goldilocks zone, not too hot, not too cold, just right for liquid water and potentially life. Statistically, even if only a tiny fraction of these worlds developed intelligent civilizations, the galaxy should be teeming with activity. Radio signals, megastructures, even the faint glow of alien cities, something should have caught our attention by now. And yet, the silence is deafening, so what's going on? One chilling possibility is the Great Filter, a theoretical barrier that prevents life from advancing to interstellar communication. Maybe most civilizations destroy themselves before they can reach the stars, whether through war, environmental collapse, or unchecked technology. If that's true, the filter could lie ahead of us, a grim warning about humanity's own future. Alternatively, advanced civilizations might abandon physical exploration altogether, retreating into digital utopias or virtual realities so immersive they have no interest in the outside universe. Then there's the zoo hypothesis, the idea that Earth is intentionally isolated, like a nature preserve, observed but not contacted. It's a cosmic version of look but don't touch, with alien societies agreeing not to interfere until we reach a certain level of maturity. Or perhaps we're simply too primitive to recognize their signals, like ants unaware of the radio waves passing overhead. The James Webb Space Telescope is now peering into the atmospheres of distant exoplanets, hunting for biosignatures like oxygen or methane gases that could hint at life. But even if we find them, the paradox deepens. Microbial life would mean the universe is fertile, making the absence of intelligent neighbors even more puzzling. What makes the Fermi Paradox so compelling isn't just the lack of answers, it's what those answers imply about us. Are we the first, the last, or is the universe hiding something far stranger? Until we know, the stars remain a silent mirror, reflecting back our deepest questions about life, survival, and our place in the cosmos. Among the countless stars in our galaxy, one behaves like no other: KIC 8462852, better known as Tabby Star. While most stars flicker gently from orbiting planets or surface activity, this one plunges into darkness without warning, dimming by up to 22% at irregular intervals. That's enough to blot out nearly a quarter of its light, as if something colossal is passing in front of it. The usual suspects, planets, even Jupiter-sized ones, can't explain such extreme dips. A planet might dim a star by 1%, but 22%, that's like expecting a pebble to eclipse a lighthouse. When astronomer Tabitha Boyajian first spotted this anomaly in 2015, the data seemed impossible. Dubbed the most mysterious star in the galaxy, it sparked a frenzy of theories. Maybe a swarm of comets, thousands of them, spiraled around the star in a chaotic dance, casting erratic shadows. Or perhaps it was a vast, uneven dust cloud, the remnants of a catastrophic collision between planets. But dust should glow in infrared light, and Tabby Star showed none. The absence of heat signatures left scientists stumped. Then came the wild card idea. What if we're seeing a Dyson sphere under construction? Proposed by physicist Freeman Dyson in the 1960s, these hypothetical megastructures would surround a star, capturing its energy for an advanced civilization. Fragments of such a sphere, a Dyson swarm, could explain the star's irregular dimming. It's a tantalizing thought, evidence of cosmic engineers at work, bending starlight to their will. Yet for all the excitement, Tabby Star refuses to follow a script. Some dimming events last days, others weeks, with no discernible rhythm. In 2017, the star suddenly faded by 8% over 48 hours, then just as abruptly brightened again. No natural phenomenon we know behaves this way. Even more puzzling, long-term observations show the star's overall brightness has been declining for over a century, as if it's slowly being drained. The mystery has turned Tabby Star into a cosmic Rorschach test. To some, it's proof we're not alone. To others, it's a call to rethink stellar physics. New telescopes like the Vera Rubin Observatory aim to monitor it continuously, searching for patterns in the chaos. But until we catch this star in the act, until we see the shadow's source, it remains a riddle wrapped in starlight. Whether the answer lies in shattered planets, alien megastructures, or something beyond our current science, one thing's clear: Tabby's star is teaching us humility. The universe doesn't owe us tidy explanations. Sometimes it gives us puzzles just to see if we're paying attention. It was an ordinary August evening in 1977 when the universe decided to break its silence just once. The Big Ear radio telescope in Ohio, sweeping the sky for signs of extraterrestrial intelligence, caught a burst of radio waves so intense that astronomer Jerry Amon circled it on the printout in red pen, scribbling, "Wow." Next to the string of numbers, that single word would immortalize the most tantalizing signal in SETI history. For 72 seconds, the cosmos blared a note at exactly 1420 MHz, the frequency of hydrogen, the most abundant element in the universe. A natural choice, scientists reasoned, for any civilization wanting to shout, "We're here." Then, as abruptly as it began, the transmission stopped. Decades of searching the same patch of sky near the Sagittarius constellation have yielded only silence, turning the wow signal into astronomy's ultimate one-hit wonder. What makes this ghostly broadcast so compelling isn't just its strength, 30 times louder than cosmic background noise, but its precision. The signal occupied a narrow band of frequencies, unlike the messy emissions of pulsars or quasars. It was the radio equivalent of a laser beam, a quality that screams artificial. Yet the very things that make it intriguing also deepen the mystery. If it was aliens, why hasn't it repeated? Why aim a 72-second message at a seemingly random spot in space? Skeptics point to more mundane explanations: a passing comet's hydrogen cloud reflecting sunlight, or a rogue satellite glinting like a cosmic mirror. But comets in the area weren't emitting at the right frequency, and no known human technology matched the signal's profile. Then there's the chilling possibility that we caught the tail end of something monumental, a distress call from a dying civilization, or a beacon that swept past Earth like a lighthouse beam, never to return. The wow signal's ephemeral nature plays tricks on our imagination. It's as if the universe teased us with a single page torn from an interstellar novel, leaving us to guess the rest of the plot. Modern telescopes like the Allen Telescope Array now monitor the region continuously, but the signal remains stubbornly silent. Perhaps the most profound lesson of the wow signal isn't about aliens at all, but about our own place in the cosmos. For one brief moment, the universe felt alive with possibility, as if we'd brushed fingers with something vast and unknowable. Whether it was a celestial accident or a deliberate hello, that lonely 72-second whisper reminds us how much we still have to learn, and how thrilling it will be when the cosmos finally decides to speak again. Black holes aren't just cosmic vacuum cleaners, they're the ultimate paradox. Imagine throwing a book into a fire. The pages burn, but in theory, if you could track every wisp of smoke and ash, you could reconstruct the story. Quantum mechanics insists information can't vanish, it just transforms, but black holes defy this rule. When matter crosses their event horizons, it's gone, seemingly erased from existence. This is the black hole information paradox, a puzzle so profound it pits Einstein's theory of relativity against quantum physics in a battle for the soul of reality itself. Stephen Hawking's groundbreaking work added fuel to the fire. He showed that black holes aren't truly black. They emit radiation, slowly evaporating over eons. But here's the catch: Hawking radiation appears random, like static noise. If the particles leaking out carry no trace of what fell in, the original information is lost forever. That contradicts quantum mechanics' core tenet: information must be preserved. Physicists have wrestled with this for decades, proposing wild solutions. Maybe the information isn't gone, just scrambled beyond recognition, like a shattered vase ground into dust. Or perhaps it's trapped in a hidden dimension, a cosmic backdoor we can't yet see. Enter the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information swallowed by a black hole isn't destroyed, it's encoded on its surface like a hologram. Think of it this way: a credit card's holographic sticker looks flat but tilted, and a 3D image appears. Similarly, a black hole's event horizon might hold a two-dimensional imprint of everything that fell inside, a cosmic thumb drive storing the universe's secrets. If true, this would mean reality as we know it is a projection, a shadow play on the edge of space-time. The stakes couldn't be higher. Solving this paradox isn't just about black holes, it's about uncovering the universe's operating system. General relativity describes gravity and the large-scale cosmos. Quantum mechanics governs the tiny world of particles, but where they meet at the edge of a black hole, the equations break down. A solution could bridge these theories, revealing a deeper framework, a theory of everything that explains reality from the smallest quark to the largest galaxy. Some researchers even speculate that black holes might be laboratories for new physics, their intense gravity warping space-time in ways that expose hidden layers of the cosmos. Yet for all the theories, the paradox endures. Experiments are nearly impossible. Black holes are too distant, too extreme, but subtle clues are emerging. Quantum entanglement, the spooky link between particles, might play a role, with information hopping from the black hole's interior to its surface via entangled particles. Others suggest black holes eventually leak their secrets through Hawking radiation, like a sealed letter slowly dissolving in rain, its ink bleeding through in cryptic patterns. What makes this mystery so captivating isn't just the science, it's the philosophical weight. If information can truly vanish, our understanding of cause and effect, of history itself, crumbles. But if it's preserved, hidden in some exotic form, then reality is far stranger, far more interconnected than we ever imagined. The black hole information paradox isn't just a puzzle for physicists, it's a mirror held up to the universe, asking us to question the very nature of existence. And until we find the answer, black holes will remain the ultimate cosmic riddle, whispering secrets just beyond our grasp. Imagine tossing 100 coins in the air, expecting them to land in a perfectly random scatter, but instead they arrange themselves in neat rows pointing northeast. That's the level of cosmic unease astronomers feel when staring at the cosmic microwave background, the afterglow of the Big Bang. According to every major theory, this ancient light should be a uniform sea of microscopic temperature fluctuations, a snapshot of the infant universe's quantum chaos frozen in time. But when scientists analyzed data from NASA Wilkinson microwave anisotropy probe and later the Planck satellite, they found something that defies explanation. The fluctuations aren't random at all. They're aligned along a mysterious corridor stretching across the sky, nicknamed the axis of evil, for the way it undermines our most fundamental assumptions about the cosmos. This isn't just a minor statistical quirk. The axis suggests the universe has a preferred direction, like a hidden arrow etched into the fabric of space, a notion that violates the cosmological principle, the bedrock idea that the universe should look roughly the same in all directions. It's as if you spun a globe blindfolded, stopped it randomly 100 times, and every time your finger landed on the same mountain, The odds of this happening by chance are astronomically low, yet there it is, a pattern that whispers either our models are profoundly wrong or the universe is playing by rules we've yet to discover. So what could explain this cosmic tilt? One radical possibility is that the axis of evil is a scar from before the Big Bang, a fingerprint of some structure or process that existed when our universe was born. Perhaps our cosmos collided with another universe in the multiverse foam, leaving a gravitational bruise imprinted on the CMB. Or maybe space-time itself is fundamentally anisotropic, stretched like taffy in one direction during inflation, creating a subtle but detectable warp. Some theorists even speculate that the axis could be evidence of a parallel universe tugging on ours from beyond the cosmic horizon, its gravity gently herding particles into alignment. The Planck satellite's ultra-precise measurements only deepen the mystery. Not only does the axis persist, but the data revealed other oddities, large-scale temperature asymmetries, strange correlations between hot and cold spots that shouldn't exist. These anomalies don't just challenge the Big Bang model, they poke holes in the very idea of cosmic randomness. If the universe were a painting, the CMB should look like Jackson Pollock's splatters, chaotic and unpredictable. Instead, we're staring at something closer to a Mark Rothko canvas, with deliberate, sweeping strokes we can't yet decipher. Skeptics argue the axis might be an illusion, a trick of interstellar dust or errors in data processing. But after years of cross-checking, the signal refuses to fade. Others propose more conservative fixes, like tweaking inflation theory to allow for slight directional biases. Yet every adjustment feels like forcing a puzzle piece into the wrong spot. It might fit, but the bigger picture stops making sense. What makes the axis of evil so unnerving isn't just the anomaly itself, it's what it represents. Science thrives on symmetry and predictability. Finding a preferred direction in the cosmos is like discovering that gravity works slightly differently when you face north. It hints at a universe far stranger, far more textured than we ever imagined. Whether it's a flaw in our models, a glimpse beyond our cosmic horizon, or evidence of something entirely new, one thing's certain: the axis of evil isn't just a curiosity. It's a crack in the foundation of modern cosmology, and through that crack, we might just catch our first glimpse of the deeper truths lurking behind the curtain of reality. In the vast tapestry of the cosmos, where galaxies cluster like cities connected by highways of dark matter, there exists a place so empty it defies logic, a spherical void spanning 330 million light-years, containing just 60 galaxies where thousands should thrive. This is the Boötes Void, a cosmic desert so barren that if you stood at its center, the night sky would appear almost pitch black, with only a handful of distant stars piercing the emptiness. Most voids in space are small, around 30 million light-years across cosmic bubbles left behind as the universe expands, but the Boötes Void is different. It's a yawning chasm of nothingness, a hole in the universe so vast it shouldn't exist under our current understanding of galaxy formation. How does a region this large end up so empty? One theory points to the violent early universe, where smaller voids merged like soap bubbles, creating an ever-growing pocket of isolation. But even that doesn't fully explain the scale. Another, more radical idea suggests the void might be the imprint of a collision with another universe, a bruise left behind in the fabric of space-time after an encounter with a parallel cosmos. If true, it would mean our universe isn't just expanding, it's bumping into invisible neighbors, leaving behind ghostly evidence in the form of cosmic nothingness. Then there's the most tantalizing possibility of all. What if the Boötes Void isn't natural at all? Some theorists speculate that a Type 3 civilization, a society so advanced it could harness the energy of entire galaxies, might have emptied this region, dismantling stars and planets for fuel over billions of years. It's a staggering thought. An entire supercluster vanished without a trace, leaving behind only echoes. Of course, there's no direct evidence for this, but the sheer scale of the void forces us to consider possibilities beyond conventional astrophysics. The strangest part, the few galaxies that do exist in the Boötes Void aren't just randomly scattered, they're arranged in a tube-like structure, as if huddling together for warmth in an otherwise frigid expanse. These isolated islands of stars might hold clues to the void's origins. Some appear younger than expected, their star formation delayed by the lack of galactic neighbors. Others show unusual shapes, stretched and warped by the void's immense gravitational loneliness. Studying them is like analyzing footprints in a desert, searching for hints of what came before. For astronomers, the Boötes Void is more than a curiosity, it's a challenge. If our models of galaxy formation can't explain this emptiness, what else might they be missing? Could there be other voids, even larger, lurking undetected in the cosmic shadows? Or is this great nothing a once-in-a-universe fluke, a statistical anomaly on a scale we're only beginning to comprehend? The void doesn't answer. It simply exists, a silent rebuke to our assumptions, a reminder that the universe still holds mysteries too big to ignore. Whether it's a scar from a multiverse collision, the relic of an ancient civilization, or simply a puzzle we haven't cracked yet, one thing's certain: the Boötes Void is the universe's way of keeping us humble. In a cosmos teeming with light and life, sometimes the most profound questions come from the places where there's nothing at all. The pioneer anomaly is the kind of mystery that keeps physicists awake at night, not because it's unsolved, but because the solution feels too tidy. Launched in the early 1970s, Pioneer 10 and 11 were humanity's first emissaries to the outer solar system, designed to sail past Jupiter and Saturn before venturing into the void. Yet as they raced toward interstellar space, something peculiar happened. Both probes began slowing down ever so slightly, as if an invisible hand had reached out to tug them backward. The deceleration was minuscule, about a billionth of a gravity's pull, but over decades it added up. By the time Pioneer 10 crossed Neptune's orbit, it was hundreds of kilometers off course, drifting like a ship caught in an unseen current. At first, scientists scrambled to explain the anomaly. Could it be dark matter clumping near the sun, exerting extra gravitational drag? Or was Einstein's theory of gravity incomplete at cosmic scales, requiring tweaks to account for this subtle discrepancy? Some even floated the idea of a long-range fifth force, a fundamental interaction beyond gravity, electromagnetism, and the nuclear forces. The implications were staggering, a crack in the foundation of modern physics, hidden in the quiet deceleration of two aging spacecraft. Then came the twist. After years of painstaking analysis, a team at NASA, a jet propulsion laboratory, traced the anomaly to something unexpectedly mundane: heat. The probe's plutonium-powered generators were radiating warmth unevenly, creating a faint but constant push in the opposite direction of their motion. It was like a car slowing down because someone left a window open, the gentle pressure of escaping air adding up over time. Case closed, or so it seemed. Yet whispers of doubt remain. The heat explanation accounts for most of the anomaly, but not all of it. A tiny fraction of the deceleration defies even this tidy answer, lingering like a ghost at the edges of the data. Could there still be undiscovered physics at play? Some researchers point to similar anomalies in other missions, like the flyby anomaly's unexplained speed changes when spacecraft swing past Earth for gravitational assists. Others note that our understanding of gravity's behavior at extreme distances is still incomplete. The universe has a habit of revealing its secrets in increments, and what looks like a solved mystery today might be the prelude to a deeper discovery tomorrow. What makes the pioneer Anomaly so fascinating isn't just the science, it's the lesson it teaches about curiosity. For decades, those drifting probes forced us to question our assumptions, to consider that even the quietest data might hold cosmic revelations. Whether the remaining discrepancy is a measurement error, an overlooked variable, or a signpost to new physics, one thing's certain: the universe loves to remind us that its rulebook is always being rewritten. And sometimes the most profound mysteries aren't in the distant cosmos, they're hiding in plain sight, in the slow, silent dance of humanity's first interstellar travelers. On October 19, 2017, a telescope in Hawaii spotted something extraordinary, a faint dot of light moving too fast to belong to our solar system. This was Oumuamua, the first confirmed visitor from interstellar space, and from the moment it appeared, it shattered expectations. Most comets or asteroids follow predictable paths shaped by gravity. But Oumuamua didn't just coast, it accelerated as it raced past the sun, as if pushed by an unseen force. No tail of gas or dust, no icy glow typical of comets. Just a silent, speeding enigma, tumbling like a flipped pancake through the void. The strangeness didn't stop there. Observations suggested an elongated shape, perhaps 10 times longer than it was wide, spinning chaotically. Natural objects rarely form like this. Most space rocks are lumpy potatoes, not cigars or pancakes. Then there was the acceleration, subtle but undeniable. Comets usually speed up when their ices vaporize in sunlight, creating visible tails. Oumuamua left no such trail. So what was propelling it? Harvard astrophysicist Avi Loeb raised a provocative possibility. Maybe it wasn't natural at all. Could this be light sail technology, an alien probe harnessing sunlight for momentum? The idea electrified the public, though many scientists countered with more mundane explanations. Maybe Oumuamua was made of nitrogen ice, a chunk ripped from a Pluto-like exoplanet. As it neared the sun, sublimating nitrogen could have given it a stealthy boost, leaving no dusty traces. Yet every explanation felt like forcing a puzzle piece into the wrong spot. Nitrogen icebergs are theoretical, we've never seen one, and the odds of spotting a random interstellar object so soon after building telescopes capable of detecting it seemed suspiciously low. Then there's the shape. Natural processes tend to make objects rounder over time, not razor-thin. Could Oumuamua have been sculpted by design, optimized for long-distance travel? The debate rages on, but one thing's certain: Oumuamua opened a new chapter in astronomy. Since its discovery, we've spotted more interstellar visitors, like the comet Borisov in 2019, a far more conventional icy wanderer. But Oumuamua remains in a class of its own, a cosmic oddball that challenges our definitions of natural and artificial. Future telescopes, like the Vera Rubin Observatory, will scan the skies for more of these travelers, hoping to catch another glimpse of whatever or whoever might be sailing the void between the stars. Whether it was a shard of an alien world or something far more extraordinary, Oumuamua's greatest gift might be the questions it leaves behind. In a universe teeming with planets, why haven't we found more objects like it? What other secrets might be hiding in plain sight, disguised as cosmic debris? For now, this interstellar messenger remains a riddle, a fleeting shadow that crossed our cosmic doorstep and vanished before we could fully understand it. And perhaps that's the most haunting possibility of all, that the universe is far stranger, far more mysterious than we've dared to imagine. We know the universe is made of dark energy, dark matter, and a tiny fraction of ordinary matter, the stuff that builds stars, planets, and us. But here's the cosmic twist: even that ordinary matter is playing hide and seek. Scientists call it the missing baryon problem, and it's one of the most perplexing inventory errors in modern astronomy. Baryons, protons, and neutrons should account for roughly 5% of the universe's total mass. Yet when astronomers tally up all the visible stars, galaxies, and gas clouds, half of them are simply gone. It's like checking your bank statement and realizing half your savings have vanished without a trace. So where is all this missing matter hiding? The leading theory paints a picture of an invisible cosmic web. Delicate threads of superheated gas stretching between galaxies, too faint and diffuse to detect with traditional telescopes. Imagine steam rising from a cup of coffee, but on an intergalactic scale. These filaments, predicted by supercomputer simulations, should contain the bulk of the universe's baryons. Yet for decades they remained theoretical, their presence inferred only by the glaring absence of matter elsewhere. Then, in 2018, the Hubble Space Telescope and the European Space Agency's XMM Newton satellite finally caught a glimpse. By studying how distant quasars' ultra-bright galactic cores filtered through the cosmic web, astronomers detected the fingerprints of oxygen ions in these elusive filaments. The gas wasn't just hot, it was scorching, reaching millions of degrees. That's why it had stayed hidden. Unlike the cool, dense gas clouds we're used to seeing, these baryons were spread so thin and burned so bright in X-rays that they'd been practically invisible. But here's the catch. Even with these detections, we've only found about half of the missing baryons. The rest could be lurking in even harder-to-spot forms, perhaps as ultra-diffuse plasma in the voids between galaxy clusters, or trapped in low-density regions where current instruments can't yet probe. Some researchers speculate that a fraction might be tied up in rogue planets or failed stars drifting in the darkness, too cold to emit much light. Others wonder if our understanding of baryons themselves needs revising. Could there be exotic states of matter or even tiny primordial black holes masquerading as the missing mass? The stakes are higher than just solving an accounting error. These baryons are the building blocks of everything we see. If they're concentrated in the cosmic web, that web structure could dictate how galaxies form and evolve, funneling gas into hungry supermassive black holes or seeding new stars. It's like discovering the invisible scaffolding behind a skyscraper suddenly. The whole architecture makes sense. Future telescopes like NASA's upcoming SPHEREX mission aim to map these filaments in unprecedented detail, hunting for the faint glow of hydrogen and other elements woven into the universe's hidden skeleton. What makes this mystery so thrilling isn't just the hunt, it's what it reveals about our place in the cosmos. We're not just searching for missing matter, we're piecing together the blueprint of reality itself. Every undetected baryon is a reminder that the universe still holds secrets in plain sight, hiding them not in distant galaxies, but in the spaces between. And when we finally find them, we won't just solve a puzzle, we'll rewrite the story of how everything, including us, came to be. Measuring the universe's expansion should be straightforward, like clocking the speed of a car with a radar gun. But the cosmos has a way of defying simplicity. Right now, two of science's most trusted methods for calculating how fast space is stretching disagree by a stubborn 9%. This gap, known as the Hubble Tension, isn't just a rounding error. It's a full-blown cosmic contradiction that's left astronomers scratching their heads. On one side, we have the gold standard, the cosmic microwave background, the afterglow of the Big Bang. By mapping its subtle wrinkles with satellites like Planck, scientists can extrapolate how fast the universe should be expanding today. Their answer, roughly 67 kilometers per second per megaparsec, meaning for every 3 million light-years you look deeper into space, galaxies appear to recede 67 kilometers per second faster. But here's where things get weird. when astronomers measure the expansion directly using pulsating stars called cepheids or exploding supernova in nearby galaxies, they get a different number, 73. That might not sound like much, but in the ultra-precise world of cosmology, it's a chasm. Imagine two scales disagreeing on your weight by 9%. You'd question the scales. But when the scales in question are billion-dollar telescopes and the fate of the universe hangs in the balance, the stakes feel infinitely higher. So what's causing the rift? Some argue it's a mundane calibration issue, like a misaligned lens skewing the data. Others whisper about something far more exciting, that dark energy, the mysterious force accelerating the universe's expansion, isn't constant after all. Maybe it's growing stronger over time or interacting with dark matter in ways we haven't imagined. If true, it would mean our universe's fate isn't just a slow, cold fade into darkness, but something far more dynamic, perhaps even a big rip, where galaxies, planets, and eventually atoms are torn apart by runaway expansion. Enter the James Webb Space Telescope, our newest cosmic detective. With its infrared eyes, Webb is peering at cepheid stars and supernova with unprecedented clarity, cross-checking both methods to see where earlier measurements might have gone astray. Early results, the tension persists, deepening the mystery. Meanwhile, theorists are racing to propose exotic fixes, extra dimensions, undiscovered particles, even the idea that we're living in a rare underdense bubble in an otherwise clumpy universe, throwing off our local measurements. What makes the Hubble tension so electrifying isn't just the disagreement, it's what it represents. Science thrives when observations challenge theory, when the universe refuses to fit neatly into our models. Whether this gap reveals a flaw in our tools or a crack in the foundations of physics, one thing's certain: the cosmos is sending us a message. And until we decode it, the Hubble tension will remain the universe's most tantalizing unsolved math problem, a reminder that even the simplest questions can have the most profound answers. There's a patch of sky that doesn't belong, nestled in the cosmic microwave background. The faint glow of the Big Bang's afterbirth lies a chilling anomaly known as the cold spot. Stretching an astonishing 1.8 billion light-years across, this region is colder than its surroundings by a fraction of a degree, as if someone left a cosmic freezer door ajar. At first glance, it might seem trivial, a statistical hiccup in the universe's thermal blanket, but the numbers don't add up. The odds of such a colossal cold patch forming randomly are less than 1 in 50. A cosmic roll of the dice so unlikely it demands an explanation. One leading theory points to a supervoid, a vast emptiness where galaxies are eerily scarce. In such a void, light from the CMB would lose energy as it traverses the expanding space, creating a cooler spot in the sky. But there's a problem: the cold spot is too big. Even the largest known voids span only a few 100 million light-years, dwarfed by this icy titan. If it is a void, it's a record breaker, a cosmic Grand Canyon with no known peers. Some astronomers argue we just haven't mapped enough of the universe to find others like it. Others suspect the cold spot is something far stranger, a scar from a collision with another universe. Imagine two soap bubbles bumping in a sink. Where they touch, energy transfers, leaving a mark. In the multiverse theory, our universe might have brushed against a neighboring one during inflation, the rapid expansion just after the Big Bang. That collision could have drained energy from our cosmos, leaving behind this frigid fingerprint. It's a radical idea, but the cold spot's sheer size and temperature drop align suspiciously well with simulations of such an encounter. Then there's the third option: inflation itself might be flawed. The theory predicts a mostly uniform universe, yet the cold spot's existence suggests patches of uneven stretching, like dough that didn't rise evenly in the cosmic oven. What makes this mystery so captivating isn't just the theories, it's the data. When astronomers scanned the cold spots region with optical telescopes, they found fewer galaxies than expected, but not enough to fully explain the temperature drop. It's as if the void is only half the story, hinting at invisible forces at work. Could dark energy be clumped here, warping space-time in ways we can't yet measure? Or is the cold spot a window into dimensions beyond our own, where the laws of physics play by different rules? The cold spot does more than challenge our models, it taunts us. Every time we think we've mapped the universe's structure, anomalies like this whisper that we're missing something fundamental. Whether it's a void-defying probability, a multiverse collision, or a crack in inflation theory, one thing's clear: the cosmos is still writing its own rules, and we're just beginning to decipher them. Until we do, the cold spot remains a frozen question mark in the sky, a reminder that the universe's coldest corners might hold its hottest secrets. Galaxies aren't supposed to defy gravity's rules, but NGC 1052 DF2 does. This ghostly, translucent galaxy, floating 65 million light-years away, shouldn't exist as we know it. Unlike every other galaxy observed, it appears to have no dark matter at all. No invisible scaffold holding its stars together, no mysterious gravitational tug keeping them from flying apart. If dark matter is the universe's hidden architect, then this galaxy is a cosmic rebel, building itself without the blueprints. The discovery sent shockwaves through astronomy when it was announced in 2018. Normally, galaxies rotate so fast that without dark matter's extra gravitational grip, their stars would scatter into the void like marbles flung from a slingshot. Yet NGC 1052 DF2 stars move sluggishly, as if gravity alone, just the visible matter, is enough to keep them in check. It's like watching a car race where one vehicle cruises smoothly without an engine, defying every law of physics we thought applied. So how did this anomaly come to be? One compelling theory points to a violent past. Picture two galaxies colliding, their dark matter halos slingshotting into space while the visible stars, like stubborn survivors, cling together. Computer simulations show such cosmic pile-ups could strip dark matter away, leaving behind a naked galaxy. Nearby NGC 1052, a massive elliptical galaxy, might have been the bully in this scenario, bullying DF2 out of its dark matter billions of years ago. But skeptics aren't convinced. Could our measurements be flawed? Determining a galaxy's dark matter content relies on precise calculations of its mass and the speed of its stars, a process riddled with potential errors. Some argue DF2 might be closer than we think, throwing off the math. Others suggest its odd structure, a diffuse, star-poor, ultra-diffuse galaxy, could mimic the absence of dark matter when it's actually hiding in plain sight. Then there's the radical possibility. What if dark matter isn't as universal as we assumed? Most of cosmology rests on the idea that dark matter is everywhere, shaping the universe from the smallest dwarf galaxy to the largest superclusters. But if galaxies like DF2 can exist without it, does that mean dark matter is more like cosmic seasoning, essential in most dishes, but sometimes left out? The implications would ripple far beyond this one galaxy, forcing us to reconsider everything from galaxy formation to the very nature of gravity itself. What makes DF2 so fascinating isn't just the mystery, it's the defiance. Science advances when nature throws us curveballs, and this galaxy is a fastball aimed straight at our assumptions. Whether it's a cosmic oddball, a measurement fluke, or a sign of deeper physics at work, one thing's certain: the universe loves to remind us that its rulebook is always a draft, open to revision. And as telescopes like JWST peer deeper into its ghostly glow, we might just find that DF2 isn't alone, that it's the first of many rebels in a cosmos richer and stranger than we ever imagined. The James Webb Space Telescope was supposed to confirm our cosmic origin story. Instead, it handed us a paradox. Peering deeper into space than ever before, Webb has uncovered galaxies so massive, so dazzlingly mature, they shouldn't exist. These cosmic elders, spotted just 300 million years after the Big Bang, are the celestial equivalent of finding a fully grown oak tree sprouting from a freshly planted acorn. Dubbed universe breakers, they're upending everything we thought we knew about the universe's childhood. Take the galaxy GNZ11, for example. Shining bright when the universe was a mere 400 million years old, it's packed with stars that by all existing models should have taken billions of years to form. It's not alone. Webb has found dozens of these precocious giants, their starlight preserved in pristine condition like fossils from the dawn of time. The implications are staggering. Either dark matter, the invisible glue holding galaxies together, behaved radically differently in the early universe, clumping faster and denser than our simulations predict, or our cosmic timeline is missing entire chapters. One radical theory suggests dark matter in the infant cosmos wasn't the sluggish, weakly interacting stuff we know today. Instead, it might have been warm, moving fast enough to collapse into galaxy-sized clumps almost instantly. Picture throwing sand into a funnel. If the grains are fine, they trickle slowly, but coarse grains pile up quickly. Warm dark matter could have jump-started galaxy formation, creating behemoths in a fraction of the expected time. Then there's the unsettling possibility that the Big Bang wasn't the true beginning. Could these galaxies be relics from an even earlier epoch, survivors of a before we've yet to imagine? Some theorists speculate about a tired light cosmos, where light loses energy over vast distances, making ancient galaxies appear younger than they are. Others wonder if gravity itself operated differently under the extreme conditions of the early universe, compressing star formation into hyperdrive. The most tantalizing clue lies in these galaxies' chemistry. Spectra from Webb reveal heavy elements like carbon and oxygen, ingredients forged in stellar furnaces and scattered by supernova. But producing them so soon requires generations of stars living and dying at breakneck speed. It's as if the early universe hosted a cosmic speed run, cramming billions of years of evolution into a cosmic blink. What makes this mystery so thrilling isn't just the science, it's the humility it demands. Every time we build a telescope powerful enough to glimpse the universe's infancy, it shows us something we didn't expect. Whether these galaxies are rewriting the rules of dark matter, exposing flaws in our cosmic clocks, or hinting at entirely new physics, one thing's certain: the universe's baby photos are turning out to be far more rebellious than we ever imagined. And with Webb's infrared eyes still scanning the depths, who knows what other childhood secrets are waiting to be uncovered? Most black holes are cosmic dead ends, places where matter vanishes forever behind an inescapable curtain of gravity. But Kerr black holes, they're the universe's ultimate escape artists. Named after physicist Roy Kerr, who solved Einstein's equations for rotating black holes in 1963, these spinning monstrosities don't just crush matter. They twist the fabric of spacetime into a vortex so extreme, it might just rip open a doorway to another reality. Picture a whirlpool in space where the water's pull isn't just downward but spiraling, creating a tunnel instead of a pit. That's the tantalizing promise of a Kerr black hole, not destruction but a cosmic backdoor. What makes these objects so special is their spin. Unlike static black holes which trap everything including light, Kerr black holes rotate at nearly the speed of light, dragging spacetime around them like a celestial mixer. This creates an ergosphere, a region outside the event horizon where space itself is whipped into such a frenzy that nothing can stand still. Here, the laws of physics get bent. Energy can be extracted from the black hole's rotation, a trick so wild it inspired sci-fi concepts like the Penrose process, where advanced civilizations might mine black holes for power. But the real magic happens deeper in. At the heart of a Kerr black hole, the singularity, the point of infinite density, isn't a dot but a ring, a loop of space-time so warped it might just stitch together two distant points in the universe, or even bridge separate universes entirely. This is where wormholes enter the story. In theory, the ring singularity could act as a throat, connecting our universe to another like a cosmic subway tunnel. The math checks out. Einstein's equations allow for such bridges, but there's a catch. To traverse it, you'd need to survive tidal forces strong enough to spaghetti-fy stars, navigate exotic matter with negative energy to prop the tunnel open, and avoid triggering a collapse that slams the door shut forever. Even if you succeeded, there's no guarantee you'd arrive intact. Quantum effects or chaotic spacetime fluctuations might scramble you into pure energy on exit. Yet the possibility remains. Kerr black holes could be nature's version of a Stargate, hidden in plain sight. The irony, we might have already found one. At the center of our galaxy, Sagittarius, a star, spins at a blistering 60% the speed of light, fitting the Kerr model perfectly. If its ring singularity hosts a wormhole, it's sitting just 26,000 light-years away, practically next door in cosmic terms. Of course, proving it's a gateway and not a garbage disposal is another matter. Current telescopes can't peer past the event horizon, and any probe we sent would be torn apart long before it could report back. That's the beauty of Kerr black holes. They dangle the ultimate sci-fi fantasy in front of us, then laugh at our inability to reach it. Whether they're cosmic shortcuts or just another dead end, they remind us that the universe is stranger than fiction. Until we crack the code of quantum gravity or stumble upon a stable wormhole, these spinning enigmas will keep taunting us with the same tantalizing question: what if? At the smallest scales imaginable, far beyond what even the most powerful microscopes can see, the smooth fabric of spacetime might not be smooth at all. Instead, it could resemble a churning, bubbling foam, a chaotic quantum sea where particles flicker in and out of existence so fast they barely register as real. This is the wild frontier of quantum foam theory, where the universe's most fundamental building blocks behave less like a calm pond and more like a boiling cauldron. The idea traces back to physicist John Wheeler, who proposed in the 1950s that at the Planck scale, a distance 1 trillion times smaller than an atom, spacetime itself becomes turbulent. Imagine zooming in on a seemingly smooth sheet of paper until you see the jagged fibers and gaps between them. Now replace those fibers with fleeting black holes and wormholes, popping into existence and vanishing in the span of a heartbeat. These aren't the monstrous black holes of deep space, but microscopic fluctuations, tiny ripples in the fabric of reality. Why does this matter? For one, quantum foam could hold the key to dark energy. Those virtual particles constantly bubbling up might exert a repulsive force, pushing the universe apart faster and faster. It's like a cosmic pressure cooker with spacetime itself as the steam valve. Then there's the mind-bending possibility that these fleeting black holes could be gateways not to other places, but to other universes, each with its own laws of physics. If true, our reality might be just one bubble in an endless froth of multiverses. But how do you prove something so elusive? Enter the holometer experiment at Fermilab. This high-precision laser device isn't searching for particles. It's hunting for spacetime's graininess, the faintest jitter in reality's foundation. By measuring whether light waves wobble as they travel, scientists hope to catch quantum foam in the act. It's like trying to photograph the individual droplets in a waterfall, except the waterfall is the fabric of existence, and the camera is a machine designed to detect disturbances smaller than a proton. If the holometer or future experiments find evidence of this froth, it would mean the universe isn't just analog, it's pixelated, a digital cosmos hiding in plain sight. Picture watching a movie on an Ultra HD screen, only to realize it's actually made of tiny, shimmering dots. Even our perception of smooth, continuous time might be an illusion stitched together from discrete, flickering moments. The implications are staggering. A pixelated universe could rewrite our understanding of gravity, quantum mechanics, and even the nature of information itself. It might explain why black holes seem to destroy information. Perhaps it's not lost, just scattered into the foam. Or it could reveal that dark matter is simply matter trapped in the wrinkles of space-time, hidden from view. This is the paradox of quantum foam. The closer we look at reality's foundation, the less solid it appears. What seems empty is teeming, what seems smooth is jagged, and what seems continuous might be stitched together from fragments. Whether it's the engine behind dark energy, the cradle of miniature black holes, or the canvas of a digital universe, one thing's certain: the cosmos is far stranger, far more dynamic than we ever dreamed. And somewhere in that froth, the next great revolution in physics might already be bubbling to the surface. Every second, trillions of invisible cosmic bullets tear through your body, and you never feel a thing. These are neutrinos, the universe's most elusive particles, so ghostly they can pass through a light year of solid lead without a single collision. Born in the hearts of stars, the fury of supernova, and the jets of supermassive black holes, they carry secrets from the universe's most violent events. Yet their reluctance to interact with matter makes them maddeningly difficult to catch. It's like trying to study a whisper in a hurricane. You know it's there, but the roar of the storm drowns it out. What makes neutrinos truly bizarre is their energy spectrum. While most are low-energy relics of nuclear reactions in the sun, some arrive with a punch, packing petaelectron volts millions of times more powerful than anything our particle accelerators can produce. These ultra-high-energy neutrinos are cosmic VIPs, their extreme energy hinting at origins in places where physics operates at its limits. The Ice Cube Observatory, a telescope buried deep in Antarctic ice, has caught a few of these rare messengers. When a neutrino finally does interact, it creates a flash of blue light Cherenkov radiation, allowing scientists to trace its path backward. Some lead to blazars, galaxies with voracious black holes shooting particle jets straight at Earth. Others point to the wreckage of exploded stars, but many arrive with no clear origin, as if the universe is playing a game of cosmic hide and seek. The mystery deepens when you consider how little neutrinos weigh. For decades, physicists thought they were massless, moving at light speed like photons. Then came the bombshell discovery that neutrinos oscillate, changing flavors between electron, muon, and tau types as they travel. This subtle dance proved they must have mass, however tiny. But here's the kicker: their masses are so small we still can't measure them precisely. It's like weighing a feather with a scale designed for elephants. This missing piece could rewrite particle physics, potentially explaining why the universe has more matter than antimatter, a lopsidedness that allowed stars, planets, and us to exist. Why does any of this matter? Because neutrinos are the ultimate cosmic witnesses. While light gets absorbed or scattered by dust and magnetic fields, neutrinos fly straight from their sources, undistorted. A neutrino from a supernova in another galaxy arrives hours before the light does, giving us a heads-up to point our telescopes. They might even carry signals from processes so extreme, like the birth of a black hole, that no other particles escape. Future detectors like the planned Ice Cube Gen 2 aim to catch 10 times more of these phantoms, painting a sharper picture of the high-energy universe. But perhaps the most tantalizing possibility is that neutrinos could be the key to dark matter. Some theories suggest sterile neutrinos, a hypothetical fourth flavor that interacts only via gravity, might make up this invisible cosmic scaffolding. If true, it would mean these shadowy particles aren't just messengers, they're the hidden architects of the universe itself. Until we know for sure, neutrinos will keep slipping through our fingers, and our detectors whispering riddles from the darkest corners of space. If black holes are the universe's ultimate vacuum cleaners, then white holes are its fire hoses, theoretical cosmic geysers blasting matter outward with unstoppable force. While black holes trap everything, even light, behind their event horizons, white holes would reverse the script, violently expelling energy and matter from a singularity that nothing can enter. The math allows for such bizarre objects. Einstein's equations even hint at their possibility, but the universe has yet to cough up definitive proof. That hasn't stopped physicists from dreaming. One audacious idea suggests the Big Bang itself might have been a white hole's grand finale. Picture this: a singularity in some higher dimensional space erupting, spewing out the raw ingredients of an entire universe in a single cataclysmic burst. It's a poetic symmetry: black holes as cosmic drains, white holes as faucets, with the universe caught in an endless loop of collapse and rebirth. Some theorists take it further, proposing that every black hole in our universe might birth a new one elsewhere, tunneling through space-time like a wormhole with a white hole exit. In this wild scenario, our cosmos could be just one bubble in an infinite foam of interconnected universes, each birthed from the remnants of another's collapse. Then there's the tantalizing link to gamma-ray bursts, the most violent explosions since the Big Bang. These beams of high-energy light, lasting mere seconds, outshine entire galaxies. Could they be white holes flickering to life and vanishing just as quickly? The energy profiles match white holes would theoretically radiate with ferocious intensity as their singularities disgorge trapped matter. But there's a catch. White holes violate the second law of thermodynamics, which dictates that entropy always increases. An object that only expels energy without ever absorbing any seems like a cosmic perpetual motion machine, defying the universe's preference for disorder. Yet nature has a habit of bending its own rules. Quantum mechanics allows for particles to tunnel through seemingly impassable barriers. Could white holes be spacetime's version of quantum tunneling on a galactic scale? Some models suggest they might exist briefly before collapsing into black holes, like cosmic geysers that seal their own vents. Others speculate that dark energy, the mysterious force accelerating the universe's expansion, could be the faint echo of ancient white holes, their residual push still shaping the cosmos billions of years later. The beauty of the white hole hypothesis isn't just in its audacity, it's in the questions it forces us to ask. If matter can be recycled through these cosmic portals, does that mean information swallowed by black holes might re-emerge elsewhere intact? Could the universe's expansion and contraction be part of a grander cycle, with white holes as the reset buttons? For now, these ideas live in the realm of pencil and paper physics, waiting for a telescope's flicker or a detector's blip to drag them into reality. Until then, white holes remain the universe's most tantalizing mirage, a reminder that for every cosmic rule, there might just be an exception. Imagine waking up one day to discover that everything, every star, every atom, even your own thoughts, is nothing more than lines of code in an unfathomably advanced simulation. This isn't the plot of a sci-fi movie. It's the simulation argument, a hypothesis that's been quietly unsettling philosophers and physicists since Nick Bostrom first laid out his infamous trilemma in 2003. His logic is deceptively simple. If future civilizations reach a level of technology capable of running hyper-realistic ancestor simulations, one of three things must be true. Either they go extinct before getting there, they choose not to create such simulations, or we're almost certainly living inside one right now, the unsettling part. There's no way to rule out that third option. Think about the universe's quirks for a moment. Quantum mechanics tells us particles don't settle on definite states until observed, a phenomenon Einstein famously called spooky. But what if that indeterminacy isn't a fundamental law of nature, just a processing shortcut? Like a video game rendering graphics only when a player looks, the simulation might conserve resources by leaving distant particles in a fuzzy, uncalculated state until measured. Even the Mandela effect, those eerie collective false memories where people swear Nelson Mandela died in prison, could be dismissed as glitches, patches in the cosmic code where updates overwrote historical data imperfectly. The argument gains eerie traction when you consider how neatly it explains certain cosmic puzzles. Why does the universe seem fine-tuned for life, with physical constants dialed to precision? Maybe because the simulators deliberately set the parameters to allow conscious observers like us to exist. The pixelated nature of spacetime at the Planck scale could hint at an underlying resolution limit, like the pixels on a screen. Even the mysterious observer effect in quantum mechanics takes on new meaning. What if our observation is just the system registering input from whatever's running the simulation? But here's the twist: the simulation hypothesis is by design unfalsifiable. Any evidence we find could itself be part of the simulation. Some physicists have still tried poking at reality's seams. One team proposed looking for computational signatures in cosmic rays statistical anomalies that might reveal a grid-like structure to spacetime. Others suggest that if the universe is a simulation, it might shortcut complex calculations by rounding numbers in detectable ways, like a calculator approximating pi. So far, no smoking gun. Even if we found one, the simulators could just patch it out in the next update. What makes the idea so compelling isn't just its audacity, but the existential questions it forces us to confront. If we're in a simulation, does that make our lives less real? Does the programmer's intent matter? And if we one day create our own simulations, does that recursively increase the odds we're also someone else's digital experiment? The simulation argument blurs the line between metaphysics and science, between creator and creation, leaving us with a dizzying realization. The true nature of reality might be a riddle we're not just trying to solve, but one we might literally be. The idea that our universe might be just one bubble in an endless cosmic froth is both exhilarating and humbling. According to inflation theory, the rapid expansion that shaped our cosmos didn't happen just once. It's a perpetual process, birthing countless pocket universes like soap bubbles in a sink. Each of these realms could operate under entirely different rules. Some might have gravity so weak that matter never clumps into galaxies, while others could collapse instantly under the weight of their own constants. In this infinite multiverse, every possible configuration of physics plays out somewhere, turning the cosmos into a grand laboratory where existence runs endless variations on its own theme. This isn't just speculative fantasy, it's grounded in the math of quantum fluctuations. During inflation, tiny ripples in spacetime could have stretched into separate universes, each with its own unique properties. Picture a boiling pot of water where every bubble rising to the surface represents a cosmos with its own distinct laws. Some bubbles might fizzle out immediately, while others, like ours, stabilize just long enough for stars, planets, and life to emerge. The so-called anthropic principle suggests we find ourselves in this particular universe not by coincidence, but because it's one of the rare few where the conditions for life are even possible. It's like winning a cosmic lottery where the prize is existence itself. But here's where things get even stranger. If the multiverse is real, some of these alternate universes could be nearly identical to ours with only the slightest tweaks. Perhaps a world where the electron is a fraction heavier or where dark energy doesn't dominate. Others might be so alien they defy comprehension, with dimensions beyond our familiar three, or forces that rewrite the very concept of time, the most unsettling possibility. Somewhere out there, a universe identical to ours in every way could exist, playing out the same history with infinitesimal variations. The choices you didn't make in this life might be unfolding in another. The multiverse hypothesis also offers a provocative answer to one of cosmology's biggest puzzles. Why does our universe seem so finely tuned for life? If there are infinite universes with random physical constants, it's no surprise that at least one would hit the jackpot, but this idea isn't without its critics. Some argue it's untestable, more philosophy than science, since we can't observe beyond the limits of our own cosmic bubble. Others counter that certain signatures in the cosmic microwave background, like cold spots or unusual polarization patterns, could hint at collisions with other universes, leaving scars in the sky. Whether the multiverse is a mathematical inevitability or a dazzling thought experiment, it forces us to confront the sheer scale of possibility. Our universe, vast as it is, might be just one note in an infinite symphony of realities, each playing its own variation on the laws of physics. And if that's true, the cosmic labyrinth isn't just a maze, it's a hall of mirrors reflecting endless versions of existence, each with its own secrets waiting to be uncovered. There's a glow in the night sky so subtle, most people mistake it for the last remnants of twilight, a pale, ghostly triangle of light rising along the path of the sun and planets. This is the zodiacal light, sunlight scattered by billions of dust particles drifting through the inner solar system, but don't let its serene appearance fool you. These tiny grains, some no larger than smoke particles, hold clues to chaotic processes shaping our cosmic neighborhood. For centuries, astronomers assumed this dust was simply debris left behind by comets, icy wanderers shedding material as they near the sun. Others pointed to asteroid collisions, violent crashes grinding rocky bodies into fine powder. But recent observations have upended these tidy explanations. NASA Juno spacecraft en route to Jupiter made an unexpected discovery, a thick band of dust near Mars, far denser than models predicted. It's as if the solar system has a hidden factory churning out dust in places we never thought to look. The mystery deepens when you consider the dust's peculiar distribution. Instead of spreading evenly, it clusters along the ecliptic, the plane where planets orbit like flour dusted across a baker's counter. Some grains even spiral inward toward the sun, drawn by its gravity, while others drift outward, pushed by sunlight's gentle pressure. This dynamic dance suggests forces beyond comets and asteroids at work. Could Mars itself be a culprit? The planet's moon Phobos, slowly crumbling under tidal forces, might be shedding material into space, or perhaps dust is being replenished by micrometeoroid impacts on the red planet's surface, launching fresh particles into orbit. Then there's the wild card, interstellar visitors. In 2017, the asteroid Oumuamua tore through our solar system, leaving no visible trail. But what if smaller interstellar objects, too faint to detect, are constantly breezing through, disintegrating as they go? Their debris could seed the zodiacal cloud with exotic minerals unlike anything native to our system. What makes this dusty enigma so compelling isn't just its origin, it's what it reveals about the solar system's hidden machinery. Every grain is a time capsule, preserving the chemistry of its parent body. Some might even contain pre-solar material, stardust older than the sun itself. Future missions like Japan's Destiny Plus aim to sample this dust directly, analyzing its composition for clues. The zodiacal light is more than a celestial curiosity. It's a reminder that even in the quietest corners of space, nothing is ever truly still. Whether it's the fallout of unseen collisions, the slow erosion of moons, or the traces of interstellar passers-by, this faint glow is a window into the solar system's restless, ever-changing heart. And as we piece together its secrets, we're not just studying dust, we're reading the autobiography of our cosmic home, written one speck at a time. Beyond the icy realm of Pluto, where sunlight is 1,000 times dimmer than on Earth, the Kuiper belt stretches like a frozen junkyard of cosmic leftovers, rocky and icy bodies orbiting in the solar system's outer darkness. For decades, astronomers expected this belt to thin out gradually, with smaller objects scattered farther and farther into the void. But the universe loves a plot twist. Around 50 astronomical units from the Sun, just beyond Neptune's gravitational reach, the Kuiper belt doesn't fade away, it plummets. This sudden drop, known as the Kuiper Cliff, is as if someone took a cosmic eraser and scrubbed away nearly all traces of debris beyond an invisible boundary. The question isn't just why the belt ends so abruptly, it's what powerful force could have carved such a clean edge into the fabric of our solar system. One leading theory points to an unseen planet lurking in the shadows. Dubbed Planet 9 by some researchers, this hypothetical world could be 10 times the mass of Earth, orbiting hundreds of astronomical units from the Sun. Its gravity might act like a shepherd, clearing out the outer Kuiper belt over billions of years, hurling objects inward or ejecting them into interstellar space. The math supports the idea. Computer simulations show a distant, massive planet could sculpt the Kuiper Cliff's sharp edge, but there's a catch: no one's found it yet. Searchers with telescopes like Subaru and Pan-STARRS have turned up empty, leaving astronomers to wonder if Planet 9 is a ghost in the equations or simply hiding in plain sight, camouflaged by the inky blackness of deep space. Then there's the cosmic demolition derby scenario. Early in the solar system's history, Neptune might have rampaged through the Kuiper belt, its migration scattering objects like bowling pins. Some were flung outward, others inward, leaving behind a stark boundary where the chaos stopped. Alternatively, the cliff could mark the outer edge of the Sun's primordial birth cluster, a relic from when our star formed alongside siblings in a dense stellar nursery. The gravitational tug-of-war between these infant stars might have stripped away material beyond a certain radius, leaving the Kuiper belt truncated. But the most tantalizing possibility, the Kuiper Cliff isn't a cliff at all, it's a doorstep. Beyond 50 astronomical units, the solar system might transition into a vast reservoir of comets known as the Hills Cloud or even the Oort Cloud's inner fringe. These icy wanderers could be too sparse or too dark for current telescopes to detect, creating the illusion of an abrupt edge. If true, the Kuiper belt's sudden end might just be the first act of a much grander, unseen structure waiting to be mapped. Enter the Vera Rubin Observatory, poised to revolutionize our view of the outer solar system. With its 3,200 megapixel camera, this telescope will scan the entire visible sky every few nights, spotting faint, slow-moving objects that have eluded detection. If Planet 9 exists, Rubin's relentless gaze could finally snag it. If not, the observatory might reveal other sculptors of the Kuiper Cliff, perhaps a swarm of rogue asteroids, a long-vanished sibling star's gravitational scars, or even evidence of a close encounter with another star billions of years ago. What makes this mystery so thrilling is its defiance of expectation. The outer solar system was supposed to be predictable, a quiet frontier where icy worlds drift in orderly orbits. Instead, the Kuiper Cliff whispers of upheaval, of hidden forces, violent histories, and perhaps even unseen neighbors. Whether it's a planet, a fossilized collision, or a gateway to deeper darkness, one thing's certain: the edge of our solar system isn't just a boundary. It's a clue. Galaxies might appear timeless from a distance, suspended like glittering islands in the cosmic dark, but zoom in, and you'll find a history written in violence. Across the universe, the largest galaxies grow not by gentle accumulation, but by devouring their smaller neighbors whole. This is galactic cannibalism, a process as brutal as it is beautiful, where colossal spirals like Andromeda and our own Milky Way feast on dwarf galaxies, tearing them apart into shimmering rivers of stars. These cosmic meals leave behind ghostly evidence, stellar streams, delicate ribbons of stars arcing across the sky like crumbs from a celestial banquet. Take the Sagittarius dwarf spheroidal, one of the Milky Way's most recent victims. Once a small but proud galaxy, it's now stretched into a looping filament of stars, wrapped around our galaxy's disk like tinsel. Thanks to the Gaia Space Telescope, which maps the positions and motions of over 1 billion stars, we've traced these stellar rivers back to their sources, and the tally is staggering. The Milky Way has consumed at least 15 galaxies over its lifetime, with some, like Gaia Enceladus, swallowed so long ago their stars have fully blended into our galaxy's halo. It's a galactic version of "you are what you eat," with each merger leaving a chemical fingerprint in the stars it contributed. But the real surprise isn't the destruction, it's the transformation. When a dwarf galaxy falls into a larger one, its stars don't just scatter randomly. Gravity weaves them into intricate structures, shells, rings, and tidal tails that linger for billions of years. The Milky Way's halo is a graveyard of these ancient mergers, a patchwork of stolen stars whose motions betray their violent past. Some, like the Helmi stream, orbit backward compared to the galaxy's spin, a telltale sign of their foreign origin. Others, like the remnants of the Kraken merger, a galaxy devoured 11 billion years ago, are so thoroughly mixed that only their unusual metal content gives them away. What's even more astonishing is how this cannibalism shapes galactic evolution. Every merger injects fresh gas and stars, reigniting star formation and even triggering the birth of globular clusters. The Milky Way's bulging center might owe its existence to a particularly gluttonous phase, where a series of mergers piled stars into a dense, shining core. Andromeda, our nearest galactic neighbor, is an even more voracious predator, its outer layers littered with the debris of dozens of consumed dwarfs. In 4 billion years, when the Milky Way and Andromeda collide, their halos will mingle like two soups poured into the same bowl, blending the remnants of all the galaxies they've ever consumed. Yet for all its violence, this process is also a form of cosmic recycling. The gas stripped from devoured galaxies fuels new generations of stars, while their dark matter halos merge into larger structures, weaving the universe's invisible scaffolding. Even our solar system might owe its existence to this cycle. Some researchers suggest the Sun formed from gas enriched by a long-ago merger, making us literal stardust from a galactic feast. The lesson here is humbling. Galaxies aren't static monuments, they're dynamic, ever-changing beasts growing through conquest and assimilation. Every time we gaze at the Milky Way's band of light, we're not just seeing stars, we're seeing the echoes of ancient collisions, the fingerprints of a universe that builds its grandest structures one meal at a time. And somewhere in that glittering haze, the next course is already falling toward us, pulled in by gravity's inexorable appetite. Imagine two coins, flipped simultaneously on opposite sides of the universe, yet somehow they always land matching heads or tails. This isn't just a thought experiment, it's the eerie reality of quantum entanglement, a phenomenon so bizarre it left Einstein himself unsettled. When two particles become entangled, their properties lock together in an unbreakable bond, no matter how far apart they drift. Change the spin of one electron here, and its partner light years away instantly mirrors that change, as if space and time don't exist between them. This isn't communication, it's something far stranger, a cosmic synchronicity that defies the speed of light and challenges our deepest notions of cause and effect. The implications ripple far beyond the lab. In 2022, the Nobel Prize in Physics went to experiments confirming entanglement isn't just theoretical, it's woven into the fabric of reality. Scientists sent entangled photons through fiber optic cables stretching over 75 miles, observing their linked behavior with flawless precision. Even when detectors were placed so far apart that light couldn't bridge the gap in time, the particles still responded in perfect unison. It's as if the universe has a hidden layer where distance is an illusion, and particles whisper to each other through a secret channel. But here's the cosmic twist. Could this quantum weirdness scale up? Could entanglement, typically seen in tiny particles, somehow influence the grand structures of the universe? Some theorists propose that the same spooky connection might help explain how galaxies align across vast distances, their orientations mysteriously correlated like entangled photons. Others wonder if dark matter's invisible grip on galaxies operates through a network of quantum links, a hidden web of entanglement stitching the cosmos together. Even black holes, those ultimate destroyers of information, might preserve it through entanglement, their event horizons encoding data like a scrambled quantum hard drive. The most mind-bending possibility, entanglement might hint at a deeper reality where space itself emerges from quantum connections. Think of the universe as a vast neural network, with each entangled pair forming a synapse, the fundamental unit of a cosmic brain. In this view, the three-dimensional world we perceive is just a shadow of a more profound, interconnected dimension where everything is linked. It's a radical idea, but one gaining traction as physicists explore holographic theories and quantum gravity. Yet for all its promise, entanglement remains a puzzle wrapped in paradox. It doesn't transmit information faster than light, no breaking relativity's rules, but it does expose a flaw in our classical intuition. The universe isn't just local, with objects only influenced by their immediate surroundings. It's profoundly non-local, with threads of connection reaching across the void, tying everything together in ways we're only beginning to glimpse. What makes this mystery so thrilling isn't just the science, it's the door it opens. Every time we probe entanglement, we're not just studying particles, we're peering into the operating system of reality itself. Whether it's the key to unifying gravity and quantum mechanics, the secret behind cosmic structures, or a signpost to higher dimensions, one thing's certain: the universe is far more entangled, far more mysterious than we ever dreamed. And in that entanglement, we might just find the next great revolution in physics. Perpetual motion machines are supposed to be impossible, a fantasy, violating the sacred laws of thermodynamics. Yet deep within the quantum realm, nature has crafted its own version: time crystals, structures that pulse in perfect, endless cycles without ever winding down. Unlike ordinary crystals with repeating atomic patterns in space, time crystals repeat in time, their atoms flipping states with clockwork regularity forever. It's as if the universe hid a pocket watch inside the fabric of reality, ticking silently long after all other clocks have stopped. The story begins in 2012, when Nobel laureate Frank Wilczek dared to ask, could a system exist in its lowest energy state, unable to lose more energy, yet still exhibit motion? The idea seemed absurd, like a car engine idling eternally without fuel. But quantum mechanics thrives on absurdity. By 2017, labs had brought Wilczek's vision to life, using chains of ytterbium ions or diamond defects locked in magnetic fields. When nudged, these systems didn't settle into equilibrium. Instead, they began oscillating between states at fixed intervals, their rhythm unshaken by external noise. The kicker: no energy entered or left the system. The crystals weren't just defying expectations, they were rewriting the rules of motion itself. Now imagine scaling this up to cosmic proportions. Neutron stars, the dense corpses of dead suns, might harbor time crystals in their crushing interiors. Under pressures strong enough to squash atoms into neutron soup, quantum effects run wild. Some theorists suggest that quirks in the star's magnetic field or the bizarre behavior of nuclear pasta, dense formations of protons and neutrons resembling spaghetti or lasagna sheets, could create conditions ripe for time crystallization. If true, these stellar remnants wouldn't just be silent tombstones. They'd be cosmic metronomes pulsing flawlessly for eons, outliving every star in the galaxy. What makes time crystals so revolutionary isn't just their defiance of decay, it's what they reveal about time's arrow. Most physical processes are irreversible, like milk mixing into coffee. Time crystals, though, are immune to this entropy. Their oscillations are immune to the universe's slow slide toward disorder, making them the closest thing we've found to eternal motion. Some researchers speculate they could form the backbone of quantum computers, their stable rhythms acting as perfect memory cells. Others wonder if they're evidence of deeper symmetries in physics, hidden layers where time doesn't just march forward but folds back on itself in loops. Yet the most tantalizing question remains: are time crystals nature's invention or ours? Lab-grown versions rely on carefully tuned conditions, but the universe is messy. If neutron stars truly host these structures, it would mean nature stumbled upon quantum immortality long before we did. And if we one day find them pulsing in the wild, it won't just be a scientific triumph. It'll be proof that the universe keeps its most astonishing secrets not in distant galaxies, but in the quiet, relentless ticking of atoms closer than we ever imagined. Picture a world where matter doesn't behave like solid particles or waves, but as something in between, a substance that refuses to fit neatly into the categories we've built over centuries. This is the realm of unparticles, a theoretical concept so bizarre it feels plucked from a surrealist dream. Proposed by physicist Howard Georgi in 2007, unparticles challenge everything we know about dimensionality. Unlike ordinary particles that occupy whole dimensions, like a dot in space or a ripple in time, unparticles could exist in fractional dimensions, flickering in and out of our familiar reality like fragments of a cosmic mosaic. What makes this idea so radical is how it redefines matter itself. Imagine trying to measure the length of a coastline. Zoom in closer, and the jagged edges reveal more detail, making the total length seem to grow infinitely. Unparticles behave similarly. Their properties shift depending on the scale you observe them, blurring the line between particle and wave. They wouldn't have a fixed mass or energy, but instead exist as smeared-out probabilities, like a fog that's denser in some patches and wispy in others. If particles are the bricks of reality, unparticles would be the brushstrokes of an impressionist painting, blending together in ways that defy rigid definition. Now consider the implications for dark matter. Current detectors hunt for WIMP or actions, hypothetical particles that barely interact with ordinary matter. But what if dark matter isn't made of particles at all? Unparticles could explain its elusiveness. Their fractional dimensions might allow them to pass through our detectors like ghosts through walls, leaving only faint gravitational traces. Some models suggest unparticle interactions could produce subtle energy signatures in particle colliders, whispers of a hidden layer beneath the quantum world we know. The hunt for unparticles is a gamble, a bet that nature's rulebook has pages we haven't even glimpsed. Experiments at the Large Hadron Collider and future neutrino observatories might look for anomalies energy that disappears without a trace or collisions that don't quite add up. Even cosmic phenomena like gamma-ray bursts or the afterglow of the Big Bang could hold clues, their light subtly distorted by unparticle interactions along the way. But here's the most tantalizing thought. If unparticles exist, they wouldn't just solve a puzzle, they'd rewrite our understanding of reality's fabric. Space and time might not be the smooth, continuous backdrop we assume. Instead, they could be grainy, fractal, or even riddled with hidden dimensions where unparticles dance just beyond perception. It's a reminder that the universe's deepest secrets aren't always hidden in distant galaxies. Sometimes they're lurking in the gaps between the particles we thought we knew, waiting to dissolve the boundaries of physics itself. 30th mystery, the neutron star's quantum soup. A teaspoon of neutron star material weighs 1 billion tons, with protons and electrons crushed into neutrons. Some theorize deeper layers contain quark-gluon plasma or strange matter that could infect normal matter. These stellar corpses are cosmic alchemy labs, forging elements we can't replicate on Earth. Imagine holding a sugar cube made of pure neutron star material. That tiny cube would weigh more than Mount Everest, 1 billion tons compressed into a space smaller than a fingertip. This is the mind-bending reality of neutron stars, the collapsed cores of massive stars that have exhausted their fuel and exploded in supernova. Under pressures so extreme even atoms surrender, electrons are forced into protons, merging to form neutrons. The result, a city-sized orb so dense it warps spacetime around it, spinning hundreds of times per second and emitting beams of radiation that sweep across the cosmos like interstellar lighthouses. But the surface is just the beginning. Dive deeper and the rules of physics as we know them start to unravel. Beneath the crust, a crystalline lattice of iron nuclei floating in a sea of electrons, lies a realm where neutrons break down further. Some theories suggest a layer of superfluid neutrons, a frictionless quantum liquid capable of flowing without viscosity. Below that, things get even stranger. At the core, temperatures may exceed 1 trillion degrees, transforming neutrons into their constituent quarks and gluons, creating a primordial soup known as quark-gluon plasma. This state of matter hasn't existed freely since the first microseconds after the Big Bang, making neutron stars the only natural laboratories where we might find it. Then there's the most speculative and terrifying possibility, strange matter. Composed of up, down, and strange quarks, this exotic substance could be more stable than ordinary matter. If it exists inside neutron stars, a single droplet escaping through a crack in the crust could theoretically infect normal matter, converting it into strange matter upon contact. This chain reaction, known as the Strangelet scenario, would rewrite the atomic structure of anything it touches, turning planets and stars into inert, hyper-dense globs of quark soup. It's the ultimate cosmic horror story, except the math suggests it's unlikely. Most models show strange matter remaining safely trapped under the neutron star's immense gravity, but the mere possibility keeps physicists intrigued. What makes these stellar corpses so fascinating isn't just their extreme physics, it's their role as cosmic forgers. When neutron stars collide, the energy released is second only to the Big Bang itself, showering space with heavy elements like gold, platinum, and uranium. In 2017, the LIGO Observatory detected gravitational waves from such a collision, and follow-up observations confirmed the birth of a literal gold mine in enough precious metals to outweigh Earth 100 times over. These events are the universe's ultimate smithies, hammering atoms into forms impossible to replicate in any terrestrial lab. Yet for all their destructive power, neutron stars might also hold clues to unification. Their cores are where Einstein's theory of gravity meets quantum mechanics, a battlefield of competing forces that could reveal how to reconcile the two. Some equations suggest their interiors might host superconductors 100 trillion times stronger than anything on Earth, or even cosmic strings, defects in spacetime left over from the universe's birth. Every pulse, every glitch in their rotation, is a coded message about the laws governing matter at the edge of impossibility. So while neutron stars may look like cold, dead relics from the outside, peel back the layers, and you'll find a seething quantum carnival, a place where matter loses all meaning, where the fabric of reality is stretched to its limits, and where the universe itself experiments with forms of existence we've only begun to dream of. Whether they're hiding quark, gluon plasma, strange matter, or something even more exotic, one thing's certain: these stellar ghosts are anything but silent. They're screaming their secrets across the cosmos, waiting for us to listen. There's a quiet terror lurking in the equations of quantum physics, one that suggests the universe as we know it could vanish in an instant, not with a bang, but with a whimper. This is the vacuum decay catastrophe, a scenario so apocalyptic it makes black holes and supernovas seem like minor cosmic hiccups. At its heart lies a deceptively simple question: is the vacuum of space truly empty, or is it just teetering on the edge of something far more unstable? Think of the universe's vacuum like a valley nestled between mountains. Right now, we're sitting in what physicists call a false vacuum, a seemingly stable low point, but not the lowest possible energy state. It's as if we're living on a ledge halfway down a cliff, unaware that a deeper chasm lies beneath. If quantum fluctuations ever knock us off this ledge, a bubble of true vacuum could form, where the laws of physics as we know them, gravity, electromagnetism, even the strength of atomic bonds, would rewrite themselves in an instant. This bubble would expand at the speed of light, obliterating everything in its path. Stars, planets, life itself would cease to exist, not through destruction, but through transformation into something utterly alien. The trigger could be almost anything: a high-energy particle collision, a random quantum tunneling event, or even the decay of a single unstable atom in deep space. Once the process starts, there's no warning, no escape. By the time the bubble's edge reached your eyes, it would already be too late. The light carrying the news would arrive at the same moment as the bubble itself. It's the ultimate cosmic checkmate. Yet here's the twist: vacuum decay isn't just doomsaying. It's a window into the universe's deepest symmetries. The fact that our vacuum has held stable for 13.8 billion years suggests we're likely in a very deep valley, with a staggeringly low chance of spontaneous collapse. Particle colliders like the Large Hadron Collider have searched for signs of vacuum instability by slamming protons together at near light speeds, probing energies that might reveal hidden fragility. So far, the vacuum seems stubbornly robust, but the mystery doesn't end there. Some theories suggest that vacuum decay might have already happened elsewhere in the cosmos, with true vacuum bubbles racing toward us from distant galaxies. Others propose that dark energy's accelerating expansion could be the first faint tremor of an impending phase transition, a slow-motion unraveling of spacetime's fabric. And then there's the haunting possibility that this has happened before, that our universe is just one iteration in an endless cycle of vacuum states, each with its own unique physics, flickering in and out of existence like bubbles in boiling water. What makes this idea so chilling isn't just the scale of destruction, it's the indifference. The universe wouldn't be punishing us, it wouldn't even notice. Vacuum decay is simply physics following its equations to their coldest, most logical conclusion. Yet in that indifference lies a strange comfort. The very instability that threatens our existence also hints at a cosmos far richer and more dynamic than we ever imagined. Whether we're living on borrowed time or in a cosmic safe zone, one thing's certain: the universe keeps its most volatile secrets hidden in the silence of empty space, waiting for us to listen. Imagine a civilization so advanced, it doesn't just inhabit planets, it dismantles them, forging a colossal shell around its star to harvest every photon of light. This is the vision of a Dyson sphere, a megastructure dreamed up by physicist Freeman Dyson in the 1960s. The concept is staggering in its ambition: a network of orbiting solar panels or a solid shell encasing a star, capturing its energy output to power technologies beyond our imagination. For a society reaching Type 2 status on the Kardashev scale, a civilization capable of harnessing the energy of its entire star, this wouldn't just be an engineering project. It would be a declaration, a cosmic billboard announcing their presence to the universe. But how would we spot such a thing? The answer lies in starlight, or rather, the absence of it. A Dyson sphere wouldn't just block a star's visible light. It would absorb that energy and re-radiate it as waste heat in the infrared spectrum. That's why projects like Glimpsing Heat from Alien Technologies, or GHAT, scan the skies for stars that glow unusually bright in infrared while appearing dim in visible light. It's like searching for a cosmic fingerprint, the telltale thermal signature of a civilization that's turned its sun into a power plant. So far, the hunt has turned up tantalizing maybes but no smoking guns. Take KIC 8462852, better known as Tabby Star, which dims unpredictably by up to 22%. Some speculated its erratic flickering could be caused by a partially built Dyson swarm, a cloud of energy collectors in orbit around the star. Others pointed to Boötes star, another oddball whose light patterns defy natural explanations. Yet in both cases, more mundane answers like clouds of dust or comets eventually took precedence. The universe, it seems, loves to tease us with possibilities just beyond our grasp. What makes the search for Dyson spheres so compelling isn't just the sci-fi allure, it's the way it reframes our understanding of intelligence. An advanced civilization might not broadcast radio signals or send probes. It might quietly reshape its star system, leaving unintentional traces in the thermodynamics of starlight. The absence of confirmed Dyson spheres could mean we're alone, or it could mean we're not looking for the right things. Maybe these megastructures aren't solid shells but diffuse swarms, their infrared signatures diluted. Or perhaps truly advanced civilizations use technologies we haven't even conceived, rendering our searches obsolete. The irony is delicious. In hunting for Dyson spheres, we're forced to confront the limits of our own imagination. Every null result is a lesson in cosmic humility, a reminder that the universe's most advanced engineers might operate on principles we've yet to discover. And so the search continues, not just for alien megastructures, but for the audacity to dream bigger, to see the stars not just as distant suns, but as blueprints for a future we're only beginning to envision. At the heart of modern physics lies a rift so profound it threatens to split our understanding of reality at the seams. On one side stands Einstein's general relativity, masterfully describing the cosmic dance of planets, stars, and galaxies through the warp and weave of spacetime. On the other looms quantum mechanics, governing the bizarre realm of particles that pop in and out of existence, entangled across vast distances. Both theories work flawlessly within their domains, yet when they collide at the edge of a black hole or the instant of the Big Bang, the equations explode into nonsense. This is the quantum gravity crisis, a puzzle that has consumed physicists for nearly a century, and solving it might just reveal the universe's deepest secrets. Take black holes as the ultimate battleground. General relativity predicts their centers harbor singularities, points of infinite density where spacetime curvature becomes so extreme the laws of physics break down. But quantum mechanics abhors infinities, insisting everything must be quantized into discrete packets. At the singularity's edge, where gravity's pull meets quantum uncertainty, neither theory can claim victory. It's like watching two grandmasters play chess with incompatible rules. The game collapses into chaos. The same paradox haunts the Big Bang. Relativity paints it as a singularity, a moment when all of space was compressed into an infinitely hot, dense point. Yet quantum physics suggests there's no such thing as true infinity in nature. Something must give. Enter loop quantum gravity, one audacious attempt to stitch these worlds together. Picture spacetime not as a smooth continuum, but as a fabric woven from tiny, indivisible threads, loops a billion times smaller than an atom. These loops interlace to form a dynamic network where quantum foam bubbles at the smallest scales. In this view, black hole singularities aren't points of infinite density, but knots where spacetime loops tangle tightly before springing back, potentially rebounding as a white hole. Even the Big Bang transforms from a singular beginning to a big bounce, the latest in an endless cycle of universes collapsing and re-expanding. The math is elegant, but the challenge remains. How do we test a theory operating at scales far beyond our current instruments? Then there's string theory, the flamboyant contender with its promise of hidden dimensions. Here, particles aren't dots but vibrating strings, their harmonies dictating mass, charge, and even gravity. To make the equations work, strings require 10 or 11 dimensions, 6 or 7 of them curled up so tightly we never notice. In this framework, gravity emerges naturally from the symphony of strings, bridging the quantum and cosmic. But critics argue string theory's beauty comes at a cost. It predicts a landscape of possible universes, each with different physical laws, leaving ours feeling like a cosmic accident. Without experimental proof, no shred of evidence for extra dimensions or supersymmetric particles, the theory risks floating untethered from reality. Yet the quest for quantum gravity isn't just academic gymnastics. Unifying these theories would answer existential questions. What truly happens inside a black hole? Was there a before the Big Bang? Could spacetime itself be emergent, like temperature arising from the motion of atoms? Some clues are already surfacing. The holographic principle suggests that all the information in a volume of space might be encoded on its boundary, like a 3D movie projected from a 2D screen. Black hole entropy calculations hint at spacetime's granular structure. Even gravitational wave detectors like LIGO might one day catch echoes of quantum gravity in the ripples from colliding neutron stars. What makes this search so electrifying isn't just the promise of a unified theory, it's the sheer creativity it demands. Physicists are crafting tools from abstract mathematics, cosmic observations, and even philosophical reasoning, stitching together patches of understanding where experiments can't yet reach. Whether the answer lies in loops, strings, or something entirely unforeseen, one thing's certain: the universe's operating manual is waiting to be cracked. And when it is, we won't just solve a theoretical puzzle, we'll rewrite the story of existence itself, from the first quantum flicker of the Big Bang to the last whisper of evaporating black holes. Dyson spheres might be just the beginning. Imagine a civilization so advanced it doesn't just capture a star's energy, it rearranges entire solar systems like cosmic Lego bricks. Take ringworlds, for example, colossal artificial bands encircling a star at just the right distance to support life on their inner surface. Picture a strip of land millions of miles wide, with sunrises engineered by orbital mechanics and gravity simulated by sheer rotational speed. The sheer scale is mind-bending, requiring materials stronger than any known element, and energy outputs dwarfing humanity's total industrial capacity. But here's the catch: such a structure wouldn't just block starlight like a Dyson sphere. It would emit telltale infrared radiation from its outer surface and cast unusual shadows on surrounding dust clouds. Then there's the Matryoshka brain, a nested series of Dyson-like shells, each radiating waste heat to power the next layer inward. This megastructure wouldn't just harness energy, it would function as a planet-sized supercomputer, its processing power so vast it could simulate entire realities or solve problems beyond our comprehension. The thermal signature would be unmistakable, a star seemingly cooling far faster than physics allows, its energy diverted into invisible computations. Astronomers have already scoured galaxy surveys for stars with missing luminosity, their light replaced by the faint glow of hypothetical megastructure exhaust. But perhaps the most audacious idea is the stellar engine, a device that moves entire stars. Civilizations fearing supernova or galactic hazards might build a Shkadov thruster, a colossal mirror offset from a star, using radiation pressure to nudge it across the galaxy over eons. The trajectory of such a star would stand out like a fingerprint, its path defying natural orbital mechanics. Alternatively, a Kaplan thruster could harness a star's own solar wind, channeling it into jets to propel the system like a cosmic sailboat. Either way, the evidence would linger in stellar motion maps, a breadcrumb trail of unnatural migration. Skeptics argue these concepts are little more than sci-fi fantasies, their energy requirements and engineering challenges insurmountable. Yet history shows humanity consistently underestimates the universe's capacity for wonder. 500 years ago, the idea of metal birds carrying people across oceans would have seemed absurd. Today, we're the ones dreaming of reshaping stars and searching the cosmos for others who might have beaten us to it. Every anomalous star, every irregular infrared glow, is a riddle waiting to be solved. Whether these megastructures exist or not, they serve a vital purpose, stretching our imagination beyond the limits of our own technology, reminding us that the universe's greatest mysteries might not be natural at all, but the handiwork of engineers thinking on cosmic time scales. As we exit the cosmic labyrinth, one truth shines clear: the universe is far stranger and more wonderful than we've dared to dream. From dark matter's ghostly grip to the multiverse's infinite echoes, each mystery peels back another layer of reality. Yet for every answer, new questions emerge, ensuring our journey never ends. So keep looking up, because the cosmos isn't just above us, it's within us, whispering its secrets to those who listen. If you've enjoyed this voyage, hit like, subscribe, and share your favorite mystery in the comments. Until next time, stay curious and remember, the universe is the greatest story ever told, and we're all part of its unfolding. The beauty of these cosmic puzzles isn't just in their complexity, it's in how they redefine our place in the grand scheme. Consider the humble atom in your fingertip, forged in the heart of a dying star billions of years ago. You're not just observing the universe, you're made of it, a living fragment of cosmic history. Every time you gaze at the night sky, you're not separate from the spectacle. you're part of the same story, stardust contemplating itself. And what a story it is! The universe doesn't just hide its secrets in distant galaxies or elusive particles. They're woven into the fabric of everyday phenomena, the way light bends, the pull of gravity, even the eerie synchrony of quantum entanglement. Science isn't about memorizing facts. It's about learning to see the extraordinary in the ordinary. The same curiosity that drives astronomers to map dark matter's invisible web is what makes a child wonder why the sky is blue. That spark of questioning is our most powerful tool, the compass guiding us through the labyrinth. So what's next? Maybe you'll be the one to crack the code of vacuum decay or spot the first definitive Dyson sphere. Or perhaps you'll simply lie back on a clear night, tracing constellations while pondering the cold spot's chill or Tabby Star's flickers. Either way, you're participating in humanity's oldest and grandest tradition, reaching beyond the known, daring to ask, what if? The universe isn't just out there, it's inviting you to explore, to marvel, and to keep unraveling its mysteries, one question at a time. Before we part ways, let's not forget the most important lesson of all. The cosmos thrives on connection. Every discovery links back to another, weaving a tapestry of understanding that spans from quantum foam to galactic superclusters. Your curiosity is the thread that keeps it growing. So whether you're a seasoned stargazer or just dipping your toes into the cosmic ocean, remember, the universe doesn't discriminate. Its wonders are there for anyone willing to look, to wonder, and to dream. Thanks for joining me on this journey through the cosmic labyrinth. If these mysteries ignited your imagination, don't let the conversation end here. Drop a comment below sharing which cosmic enigma captivates you most. Is it the phantom pull of the Great Attractor, the haunting silence of the Fermi Paradox, or something else entirely? And if you're hungry for more deep dives into the universe's secrets, hit that subscribe button so you never miss an adventure. Until next time, keep your eyes on the skies and your mind open to the infinite possibilities waiting to be discovered. The cosmos is vast, but it's yours.